Okay, so we're going to move now into the diagnostic session, and it's with pleasure I'm introducing Marc Lipsitch from the Harvard Chan School of Public Health. Hopefully you can hear us. He's going to talk about everything keeps changing, lessons from COVID-19 about surveillance and diagnostics. So take it away, please, Marc.
Thank you. Can you hear me okay?
Yep, we can hear you perfectly.
Great, and you can see slides?
Yep.
Terrific. Well, thanks for the invitation. I'm sorry not to be there in person, but I'm glad to, I think I heard James Hayes' distinctive voice over the thing a few minutes ago, so it's nice to see people virtually. I'm going to talk a little bit about surveillance and diagnostics, which are two very closely related topics, and I'm going to use them almost interchangeably, thinking of diagnostics as the tool in public health by which we do surveillance, not the only one, but one of the key ones. And I'm going to talk sort of back and forth between these two related topics. I also have a disclosure that I am speaking in my academic capacity today, not in my still ongoing role with the US CDC. And the work I'm going to talk about today has just been published, some of it in this paper on the left, and a little bit further ago, a couple of months ago, on the paper on the right. And these are some of the people that have influenced the thinking and been thought partners. And we have another piece that is on medRxiv that also relates to some of these topics. So if people are interested in more, these are some sources, and I'll share the slides after. With Mauricio Santillana and other colleagues further back, we tried to, before the COVID pandemic, and really actually in the aftermath of the H5N1 pandemic, H1N1 pandemic, sorry, H5N1 pandemic, not doing prophecy here. We tried to kind of put a structure on what it is we need to know in pandemics and what the surveillance inputs to that would be as ways of developing evidence. And it sounds, from what I could tell, as if much of the discussion in the past little while has been on some of these questions about evidence. And this is a highly rational and idealized picture of how surveillance develops. It's often much more complicated than that in practice because of systems being developed for one reason and repurposed in emergencies for another. But there is sort of a rationale that decision makers need to make decisions. To inform that, we need some kinds of evidence on things like the transmissibility and severity and other features of a pathogen during a pandemic, and that various types of inputs can help to inform that. A lot of people outside the public health field often use surveillance as if it's a single thing. The word surveillance as if it's a single thing. And I think one of the really clear things that came out of the COVID pandemic that was known to some before, but really clarified, is the notion that we have lots of different purposes for surveillance. And these are not all the same, and the systems that are well suited to one may be very poorly suited to another. And so I'm going to give some examples of that in the next few minutes. A related concept that we put forward in the article on diagnostics with Jonathan Grad is the notion that diagnostics too have different purposes and different desirable characteristics. The ideal diagnostic would be highly accurate, rapid, and cheap. And that's rarely possible. That is, of course, the ideal, but more often we have trade-offs. And we can think about some of those trade-offs and which ones are most important to satisfy in different contexts. So in the case of screening for public health, where you're using it as a control measure, you need low cost and rapid turnaround time so that you can use lots of them and use them and get people the information quickly. Whereas with some other types of questions that we try to inform, such as severity measures and informing treatment, accuracy is much more crucial than say turnaround time or low cost. So implications of that principle are that the criteria for use should inform licensing rules. And this is not generally true, at least in the United States and in other places. Typically, licensing is based on use suitability for clinical care, but tools that are really good for clinical care because of extremely high accuracy may be bad for surveillance and vice versa. So we need actually work to help inform the rules for licensing. We also need statistical work and education of epidemiologists to account for test characteristics at different stages of outbreak. So much of the challenge in COVID early on in assessing severity, for example, was due to using serologic tests that had poor positive predictive values because they were not hugely specific, and those then inflated the numbers of cases that were being detected. And that's a particular problem early in an outbreak. This is the sort of knowledge that an epidemiologist working in the field understands, but that is sometimes very hard to communicate. Thinking about the problem of detecting a new pathogen, we can ask why that's important. And we heard about the 100 Days mission and the need to rapidly activate countermeasures. And I think that's the most important reason why early detection and accurate detection is important. And in COVID, we also saw the need to prepare for the spread of new variants, which in a way were like their own little new pandemics each time we have had a new major variant. So if that's a goal, then how do we do it? Well, one of the key ingredients for detecting new pathogens and new variants is geographic scale. COVID taught us lots of lessons, some of them easier to understand than others, but one of the really good ones it taught us was by having the first 4 variants appear on 4 different continents. It showed the real importance of having large geographic scale for our surveillance systems. And for detection, that's really absolutely essential. On the other hand, size and the number of isolates characterized shows diminishing returns. You obviously need to have enough surveillance to detect new things, but the value of detecting of larger and larger samples for detecting new variants or new pathogens goes down with the size. And there's a famous rule of 3 that gets published in the literature about every 20 years. And the rule of 3 says that if you want to detect something at a frequency of 1%, you need to measure 300 samples. If you want to see it at 0.1%, you need to measure 3,000 samples and so forth. So 3 over the number, over the proportion that you're trying to detect. What about quantifying burden? A completely different thing. So you already know something's here. You're not trying to find the first one, but you're trying to figure out how much of it there is and whom it's infecting. In COVID, we saw lots of applications of this, from just general situational awareness to identifying inequities and trying to understand who was infected and why they were becoming infected, and sort of everything in between. So obviously, quantifying the burden is essential. But what are the main characteristics of a surveillance system that's good for that? The most important of these is representativeness. The notion that the people that one is sampling are a random sample or a nearly random sample of the population, rather than, say, those who are seeking care. And very few countries got that right. The UK was certainly the leader globally in having 2 very large and very impressive studies that measured representative samples. This is a graph from Luxembourg that also did so quite effectively in a much smaller population. A related question, or a related value in such surveillance systems, is data completeness. So having not only the number of people who are positive, but how positive they were, what the PCR CT value was, who they were, demographics, how severe their cases were, and so forth, because the value of those data together is much greater than of each piece separately. And that's exemplified by some work that we did that James Hay and Untitled Grad and Michael Minna led, rather, that showed how you could use CT values to reconstruct trends. And those were values that often were never reported because they were thought to be not very interesting for epidemiology. But it turns out that they can be of some great value for epidemiology. So in the United States, we learned this lesson essentially by failing it, the lesson of the importance of representativeness. We and many other countries relied on reported cases and sometimes hospital admissions as our major measures of whether we of what we how many cases there were. And the problem with that is that prevalent cases or incident cases, which are what we're interested in, are put through many filters, figurative filters, as we try to measure them by the very imperfect measure of reported cases. So a second principle for surveillance and for diagnostics that we suggested in the recent piece was to set up systems to sample randomly from the population. And as I say, the UK is really the place where that was proven valuable most clearly. This is a partial list of some of the things that that those random samples were able to do, not just to show the prevalence of infection, but to show the appearance and growth of new variants, to find evidence of reinfection, and importantly, to inform equity measures by comparing across groups whether the disparities in their outcomes were due to higher rates of infection, which was, as it turned out, a major cause, or more due to differences in healthcare access or healthcare quality, which may have been a contributing cause. Another principle is that classic diagnostics and healthcare data are not the only source anymore. We now have people's digital online trails. We have data from wastewater, and we have data from healthcare. And each of these is complementary in terms of its cost, has complementary benefits and downsides in terms of cost, widespread availability, ease of collection, and invasiveness, and sort of how much it compromises privacy potentially. And so the combination of these three is types of data, and others as they come online is going to be much more powerful than individual types. As an example of this, from the work of the CDC Center for Forecasting and Outbreak Analytics, they were able to show that the predictive power of a forecasting model of hospital admissions was improved by incorporating wastewater data, particularly at times when it had been flat for a long time and was about to change. So on the left is the forecast with no wastewater data, and you see continuing the flat trend is predicted to continue while the data points are going down. But the wastewater as a leading indicator can help to make those predictions better, as they showed in recent work. Another principle is to keep up with pathogen evolution. And this is important because diagnostic tests can lose their sensitivity and need to be updated if they're not detecting new variants. And also very important is to link the other types of data to variant identification so that one can learn about the characteristics of new variants. And that we actually made a separate concept or a separate principle in our article, the need to link multiple data types. Unfortunately, as I mentioned, different surveillance systems collect different types of data and rarely link them. But the value of seeing, say, the number of severe outcomes stratified by variant or by age of the person or by their demographic history or their clinical history massively improves the value of each of those types of surveillance. As an example of that, some work we did with Kaiser Permanente Southern California in my CDC role was to take their linked database, so they are a healthcare provider and payer as close to a healthcare system as we have in the United States, which keeps longitudinal records on their patients. And so they were able to take the individuals who are diagnosed with COVID-19 specific to one variant or another, and estimate the comparative severity of Delta and Omicron variants in the first instance, then different variants of Omicron. And then that process has been repeated as new variants have come up several times now. We're on our fourth round of this effort to try to compare severity of different variants as new variants come into the population. So that's sort of the last thing I wanted to say, is that we need to have a sort of surveillance mindset for what used to be called research. We need to set up systems that can be used periodically or continuously, and expect that the quantities that we measure, not just the number of cases, but the severity of the cases, the demographic groups affected, the vaccines effects, and so forth, are all going to be changing over the course of multiple parts of the pandemic. And so pandemic surveillance really needs to be a sort of continuous or repeated version of what we usually call research, that produces single papers that produce estimates of numbers. So in the old days, we used to think of all these things on the left, like severity and transmissibility, as parameters that we estimate once. But now with COVID, we've seen that each of them changes because the virus is changing and the population is changing. So I've gone a little bit over, and I'll stop just on this summary slide and take a question or two. Thank you.
Okay, thanks very much for that fantastic overview and introduction. Any questions in the room?
Thanks very much. So I just wanted to pick up on that point you were making about identifying pathogen evolution in real time. So I saw you sort of included some SG target failure data, and I sort of feel I should remind the room that that's a bug that was turned out to be useful as a feature in COVID. Most commercial providers of assays don't give us information on the primers and probes that they're using, which means that it's very difficult to know, number one, if an assay starts to fail, what evolution we're identifying, and vice versa. If you know that evolution is present, being able to work out which assays are going to fail. What can we do about that?
Yeah, I think that you're right that S-gene target failure is not a success strategy. It was a coping strategy, and it's not going to happen the next time that we have this wonderful thing that keeps changing and telling us what variant we have. I think some work that we did with Jonathan Grad and Ali Hicks in the past suggested that one approach, which we were talking about in the AMR context, for sequence-based diagnostics, but applies more broadly, is that for every time you, for every some number of negative tests that you get, you should perform the sort of gold standard test, which in this case might be sequencing or might be, in the antibiotic case, might be sensitivity testing. Phenotypic sensitivity testing. And the idea there is that you need to sort of keep finding out if your diagnostics are working, and if the thing you're worried about is that they miss true positives, then you need to test some of the negatives periodically. And again, this is a particularly infectious disease-like problem. Nobody goes and checks, blood glucose tests to find out if they still work on the people of 2024 when they worked well in 2023. We're the same people, but the microbes are not the same, and so you have to keep testing these diagnostics by some gold standard. It's harder, of course, if you don't have a gold standard, but usually there is something like sequencing or phenotypic testing.
Thank you. Yeah, next question.
Thanks, really nice talk. I'm particularly interested in your recommendations of combining different disparate data sources together. And the obvious challenge there is that they'll all be collected in slightly different observation processes. So I wondered if you had any general comments on how we should be consistently or as a community better doing that on a more similar basis, or ensuring that we extract the right signals and discard the noises in those data sets.
Yeah, I think, I mean, part of the beauty of that approach is that it uses signals that people are collecting for all sorts of reasons. So I think it's risky to try to, or it's a limited strategy to try to say you have to collect them this way for us, because usually they're not collected for us, or many of them are not collected for us. So I think where possible, standardizing collection, of course, is beneficial, but I would perhaps say that it's a problem for the modeling and statistics communities to try to solve, to figure out how you combine data sources from different sources of different types. And there's been a lot of work, especially in the UK, on Bayesian evidence synthesis. That's sort of one approach. There's certainly other ways to think about the problem, but I think setting up standards for people that they have no incentive to follow is is not the primary means I would use. I think I would throw technical work at it more.
Yeah, James.
Mark, thank you very much for a very interesting talk. I think, if I can paraphrase your talk, you've described approaches that would be suitable in high-income settings. I wonder how you would prioritise all of these approaches. If it's possible to give a succinct answer to this in the other end of the scale, in low-income settings, such as where we think it more likely for pandemics to arise.
Yeah, well, I think where they arise and where they cause the most harm are potentially the same and potentially different places. So I think I would again separate it by sort of stage. And I think for the tracking part, I mean, I think people sometimes see studies like the ones the UK did as luxury items, and maybe on that scale they really are luxury items. But if you think about the quantity of decision relevant data they create, and in particular, I mentioned it briefly, I didn't have time to go into it, but we talk about it in the Frontiers paper a little bit. In particular, data that is of importance in reducing health inequities and in serving the least advantaged members of the community, they are incredibly valuable. So I think I would push harder than maybe some do for the value of random samples. They may not need to be as big and they may not need to be as comprehensive, but really understanding who's getting infected is kind of preliminary to any other control measures. And case-based reporting rarely does that with a pathogen, at least a pathogen like this one, where there's a lot of low and asymptomatic infection. So I would probably put an extra thumb on the scale for that approach among the others that I talked about. I also think it's important to mention that with some of these things like severity and sequence, we don't need it everywhere. With other things and vaccine effectiveness, we don't need this. We don't need high quality studies everywhere if some of the settings have access to better data and the same kinds of phenomena. So much of the world relied on Israel, to some degree the UK, Qatar, and a few other places for vaccine effectiveness. And, you know, as someone who's arguing for better public health funding, we can use that and say we shouldn't be relying on other countries for our surveillance. But in fact, much of that data didn't need to be collected in every locality. It needed to be collected in some places with high quality. Of course, if the vaccines are different or the population is very different, then you need local data. But I think it is worth just saying that not everything needs to be measured perfectly everywhere.
Okay, thank you very much. We'll move on.